We will discuss our findings of the LCA we have performed on the conversion of chicken manure to biofuel. The findings will be compared to a previous LCA study on co-fired rapeseed to biofuel. We will analyze and discuss which one has less impact on the environment. The functional unit we use in our model is the 1 kilowatt hour electricity output per user. The functional unit is important to be defined correctly in order to make an accurate comparison of the environmental impacts from the process of burning chicken manure and rapeseed oil in creating electricity. We have created a set of assumptions. Most importantly, we assume that chicken manure is not a valuable good, and therefore no emissions and impacts are allocated to the chicken manure. Another important assumption is that the carbon emissions during combustion of chicken manure is designated as biogenic. This is because the carbon comes from plants, which will go back in a sort of cycle. We will discuss some more assumptions while discussing the flow diagram in the next slide. In defining our system boundaries, we only focus on the primary activities and emissions related to the process of electricity production. We did not take into account human activities associated with the production, as well as facility construction where the process takes place.
Here you can see the flow diagram on which your LCA is based. The process is as follows. First, there's transport of the chicken manure from the chicken farm to a storage facility. Next, you have the drying of the chicken manure in a drying facility. And afterwards, it gets combusted in a power plant and electricity is generated with an overall 42% efficiency. This electricity is then transported to the user with another 4% loss. Other assumptions in addition to the previous are the following. No transport is needed between the storage, drying and combustion process because we assume they are undertaken on the same industrial site. Also, we assume a 16-ton lorry is used to transport the chicken manure. Furthermore, we assume we need the same amount of electricity for storing chicken manure in comparison to storing rapeseed. And last, we also assume that water that comes from the drying process is also an emission. The most important results of the analysis are shown here. The contribution to global warming of the whole life cycle of the conventional energy mix turns out to be the highest of the three alternatives. Electricity from rapeseed comes second. Chicken manure has the lowest impacts, which is 4 times lower than conventional energy sources. A closer look at the two sustainable alternatives gives insight in the stages of the life cycle that contribute most to their impact. First, coal-fired rapeseed oil. 2/3 of the global warming potential of this process is caused by N2O emissions. These emissions are associated with nitrogen fertilizer. We can even conclude that these quarters of the 3/4 of the impact are the result of fertilizer production and use. The process that uses chicken manure shows a different picture. A large part of the impact, over 40%, can be assigned to the emission of methane during storage. Together with methane exhaust during the drying process, more than half of the global warming is caused by this gas. Transport is also a significant contribution. There are some possibilities for improvement. Because we assume the electricity is generated next to the drying process of the chicken manure, it could be possible to transfer the waste heat back to the facility where the chicken manure is dried. We have calculated enough waste heat is generated to supply the drying facility of heat, which is 340 megajoules needed versus 6300 megajoules of waste heat. This would save all carbon emissions coming from the drying of the chicken manure, which accounts for 13% of the global warming potential. Furthermore, it would be worthwhile to try to capture the methane emissions during the storage process. These methane emissions account for 41% of the total global warming potential. A first general limitation of performing an LCA is the following. Because you have to take into account a margin of error due to various limitations such as difference in data quality and absence of potentially important data, in general no conclusion can be made on LCA results. Therefore, you can argue at what order of magnitude one production process has lower environmental impact than the other. The second limitation regards the validness of the assumptions we made. For instance, we assumed no impact from process at the farm is allocated to the chicken manure, because we assume it is pure waste. But this is a valid assumption. And also, can we assume that chicken manure is not transported between the stages of storage, drying and combustion? Will this decision, for instance, have an effect on the overall results? These decisions is also to do with the third limitation, that is, insufficient knowledge of the whole system results in a more simplified representation of electricity production from chicken manure. This represents the constant dilemma you face while performing an LCA. A simplified representation is easier to create, but the results are less precise. On the other hand, a more precise data requires the LCA to be more complex and thus is more time consuming. The question remains, what is the most optimal way to perform an LCA? Thank you for listening.